Welcome to the Computer Science Distinguished Lecture Series. I'm Justin Wen. I'm a faculty member and also the host for today's speaker, Professor Tony Chen from Hong Kong University of Science and Technology. And I'm happy to introduce our distinguished speaker today. Tony actually has a long CV. It will take me a long time to go over all the contribution achievements. So I just try to highlight a few things about our speaker. Okay, so to describe him, okay, so I would use one word, diverse. Okay, so this is, I think, one word, a very good word to describe him as a scientist and other areas. So diverse in the sense of academic background. So he got his engineering degree from Caltech, and then a computer science PhD from Stanford University. And then he became the professor in mathematics in UCLA for more than 20 years, I believe. Actually, we have a few faculty members from their alumni of UCLA as well. Anyway, so he's also diverse in terms of research area. So he worked on linear algebra before, and also, if you ever work on this area, okay, so one famous result that he did was circling preconditioner. And also numerical methods for solving differential equations, multigroup methods, domain decomposition methods, etc. And then in the last 20 years, he has been working on the area of image processing. If you take a course or try to use image processing methods, then you will probably use one of his methods. For example, okay, I just want to mention, because there's many, okay, the active contours without edges paper, it's a well-known method. In fact, it's called convex model these days, and used in practice, especially in the medical imaging, in other applications, and it's actually received the best paper award from IEEE signal processing in 2003. And he also is a distinguished scientist in the area of scientific computing. He is a member of the US National Academy of Engineering. He's also a SCIEM Fellow and AAAS Fellow as well. And well, for people who know him, okay, so he's one of the most cited mathematicians, okay, in the world. He also made a lot of contribution to the scientific computing community. He organized, he served on the editorial board, many like SCIEM journals and etc. And also he organized many conferences such as the Householder Meeting, as well as the AMS Millennium Conference in the year 2000. But in the meantime, he's also active in research, and also he's active in administration. So during I was a student at the UCLA, so he first started as just a regular faculty member there, and then he became the graduate chair, and then chair of the department, and then later on, he is a co-founder and also the director of the IPAN, Institute of Pure Applied Mathematics at UCLA. It's an NSF-funded institute. And then he became the dean of physical sciences in UCLA, and then continue to move on to assistant director at NSF in the US. And finally, now he is the president of the Hong Kong University of Science and Technology. Just want to make a personal note, okay, so in case you don't know, okay, so Tony was my PhD supervisor, so I was his student. And as a student of Tony, so one thing that I had to deal with is the where to meet him. So from his regular office to the graduate chair office, to the chair's office, to the dean's office. I just have to keep track of the location. And not just that, I have to keep track of the time too. So my waiting time from seconds to minutes and to hours, okay, depending on his schedule. Now to meet him, actually, really I have to make weeks in advance. Another note I want to make is that, okay, so in the last 20 years, okay, Tony has been working on image processing, actually has a very successful career in this area. And that's also the time that he is actively involved in all these administration duties. So I don't know how he did it, but he did. So finally, okay, I just want to say a few words about, he's now the president of Hong Kong University of Science and Technology. In case you don't know about the university, well, he brought some brochures, okay, so you can welcome to take one from here in the back. Now, if you have never heard of, Hong Kong Science and Technology, Hong Kong University of Science and Technology, just give you an idea, okay? So there are many rankings about universities in the world right now, and one ranking is the QS ranking. Actually, I'm not sure where it is from, but from some.
London. London.
From London, okay, I think it's respectable, okay, ranking. And so Hong Kong University of Science and Technology, the World University ranking is number 28. That's very, very high. And the World University ranking in computer science is number 8. Just follow the top one. So it's a very, very high-ranking university. So I think I'm done here. That's enough time. So let's pass the time to Tony. So please.
Wow. Thank you very, very much. I'm overwhelmed. Okay. To me, talking about HKUST, I always think about HKUST as the Waterloo of Hong Kong. Okay? Because your university is famous for its computer science department, but science and engineering in general. And that's what we are. We do that. But we have a business school. I understand you don't have a business school. And so there's, in a way, the topic of today is also, there's no better place for me to do this, in a way. Because you can see from what Justin has said, I'm a card-carrying computer scientist. I'm one of the early vintage, okay? In fact, when I studied computer science, most universities in the US did not have a computer science department. There were no undergraduate majors, okay, including Stanford. There was no computer science major. People think it was a passing fad. Why would you study a machine? What's so science about it? This is 40 years ago I'm talking about. So if you roll back the clock and you now fast forward, what is happening today with computer science is unimaginable, okay? So I assume most of you are related to the department or the faculty in one way or another. You are in the most exciting time, in a way, especially young people among you. The future is limitless. So here I understand you have computer science, you have mathematics, you have statistics, you have applied pure mathematics all under one roof. And I'm that person, okay? So I don't have explained to you. Typically there's always a little bit of political infighting, a little turf. You go to some university, statistics is part of math, statistics is not part of math, computer science. I can tell you when I was at Stanford, computer science, when I studied, was in the College of Letters and Science. When I left, is in the College of Engineering. So now I am an alumnus of engineering at Stanford. I never went there, okay? But I think that change tells you a little bit. If I was walking around, I noticed David Cheriton's name, and he's sort of my vintage. We never overlapped because I think we were about the same age, but I knew about him because he's a famous professor at Stanford. I think even in those days, Google, all these things was just like science fiction, really, in a way. So this is obviously a cross-section topic, as you heard. 20 years ago, I didn't know anything about image processing, okay? I knew actually relatively little about the mathematics involved in this kind of image processing. I had to learn it myself. But I was driven by the excitement, the possibility in this field. And there are many young faces here, I tell you. So for you, it will be a new challenge. I can tell you in fact, I spent my sabbatical in 1994, 95. And I took that sabbatical and I learned about this field. That's what sabbaticals are for, right? So I went back to UCLA and I said, okay, now I'm going to write a proposal to NSF, okay, to do this. Well, I've never failed an NSF proposal until then, okay? Because I wrote this proposal, I said, I want to use this kind of new mathematics to do image processing. The reports came back, what is this thing? I'm trying to use partial differential equations to solve image processing. We have pixels, we have, images are discrete. So, why would you do this? It won't work. We don't understand it. So they didn't even get past my abstract, okay? So the sense of rejection the sense that I've chosen something wrong, okay, is bad. But I was pretty sure this is the right way, okay? So I took the referee report seriously. I anticipated the question. I try again next year, and the rest is history, so to speak. Okay, so I think there's a lesson in there for every one of us. Okay, so I want to acknowledge, I mean, these are, he was a postdoc of mine. He was a student. He's passed away, unfortunately, last year. And she was a postdoc of mine, but now she's a professor at UCLA. I don't know. So I work with many, many other students and postdocs, but these three helped me when I first gave this talk 3 years ago at the SIAM national meeting. SIAM in 2012 turned, SIAM, many of you know, Society of Industrial Applied Mathematics. It celebrated its 60th birthday in 2012. 50th? 60th? Same age as me, so I remember. So I was one of the speakers, and this is the talk I gave. Frankly, I'm not as active in research, okay, but this is a survey talk. I assume most of you are not familiar with this area. I talked to Justin, and he said, don't worry, just give the overview, give the excitement, and you know, I'm not talking to the technical expert, and that's not the point, okay, so bear with me in that. So let me tell you a little bit about imaging science, okay? I told you 20 years ago, of course people were doing imaging science. Right? It's part of signal processing. Typically it's done in electrical engineering departments, voice, you know, and images, it's a signal. And sometimes in computer science department, but mathematicians never know what it was, okay? I mean, in those days. Relatively new to the math community. But starting about 2007, there was this journal in SIAM that was founded. And I'd show you a little bit. I was involved in doing that. It's called SIAM Journal of Imaging Sciences. When it came out, there was a lot of doubt about whether SIAM should get into this, okay? Just like there were doubts about whether, I'm sure Stanford said, should we form a computer science department? There were a lot of people against it, okay? I can tell you, okay, similar. But shortly after, a few years ago, it was in terms of impact factor, it was number 2 in SIAM. I think number 1 is SIAM Review, which is, you know, everybody required to get one. Every library is supposed to have one. You have IEEE, signal processing, you know, transactional image processing. You have some more specialized journals, computer vision, mathematical imaging and vision. These are, I think, European-based. And then you have some other things that are, you know, lecture notes and so on. So here are some of them. Now, there has been some thing going on more recently. There's SIAM now, has either biannual, I think every 2 years, it has an imaging science conference, or here was one in 2012, and there was some more after that. IEEE, of course, has ICIP, International Conference on Image Processing. I think it's yearly. In a way, for people in applied mathematics of a certain vintage, a big motivating framework for computational mathematics is computational fluid dynamics. So not only because it has obvious application, but because of its complexity, because of its challenge. You know, multi-dimensional, it can be very high dimension, it's moving, it's non-linear, it has crazy things like turbulence, nobody understands. So that has motivated a lot of applied mathematics from basically the Second World War, okay, on. Von Neumann, people like that were trying to solve that problem. So in a way, image processing in the last 2 decades has sort of taken a little bit of that role. And that's sort of the basis of my talk. The role is in the sense of, obviously you can use mathematics to help solve some of the image processing problem. But it's not only one way. Image processing also motivates a lot of the interesting mathematics. It's still going, but I try to indicate some examples of going both ways. That's the idea. Okay, I have to go here. Oh, thank you. I give this is wireless. Okay, okay, Bluetooth. Okay. I told you I was involved in this SIAM journal. I want to tell you a little historical context. 2006, if I remember, there was a SIAM conference in New Orleans. It was 1 week before Katrina. Okay, so I remember we said, wow, you know, you were there 1 week late, we will never be given, you either get there or get out, basically. So at that meeting, SIAM decided, hey, let's explore whether we should have an imaging journal. And I was asked together with Kirk Jordan, who was at IBM Research, to look at this. And so I think Katrina was 2005, maybe, yeah. So a year later, we did this work, we did a survey and all that. So we submitted this report, proposal for a new SIAM journal of imaging science. Okay, this is only less than 10 years ago. But that's that was my notes. Yeah, I forgot, actually, I never looked at this. Well, but anyway, the point is there was some of you may recognize some of these names. So SIAM, the board, finally decided to do this. Because SIAM is worried about whether there's a market, whether it would lose money. It's a business decision, whether there's a demand. Okay, okay, please. So as late as, you know, 8, 9 years ago, even SIAM was not sure that they wanted to do this. Another indication I want to tell you. So in computational math, I was giving another talk recently, and I did my own internal H-index, okay, citation thing. So I kind of know, say in the last 20, 25 years, what are some of the most cited papers? And today, very easy. You just go on Google Scholar and you just type. And this is not scientific, okay? I'm pretty scientific, okay? So not exhaustive. So I look up, these are the top 10 most cited recent computational papers. Recent means in the last 20, 25 years. So, you know, I even list some of the old ones, like conjugate gradient, 1952. That's how many citations. I checked it 2 days ago, right? The Monte Carlo casino method, right? The Monte Carlo, you know, that one was done even about the same time. It had actually 30,000 citations. Still today, people refer to it, okay, for simulation. Golub Van Loan, many of you know, the book on matrix computation, 50,000, 52,000. Okay, so these are books and classics, so you know you can't really compare to them. But here's the more recent one. So I want you to look at them. So these paper, almost 14,000. A typical paper in mathematics, you'll be lucky to have over 100 citations. Okay, so in applied math it's a little bigger, but still, it's very rare that you have more than 500. But this is because the community is not that huge, and it takes a lot of technical skill to even read and understand the paper. So, you know, it limits the audience. So, two things I want you to know. First of all is, if you look at this, by the way, this paper that Justin mentioned, I barely made the top 10. So, yesterday, 2 days ago when I was checking, maybe I fell out of the top 10. Okay, so this is a huge number for me. But look at this. But if you look at this list, majority of these are related to image processing. That was my point. Obviously, compressed sensing, if you don't know, I will have an example of that. You know, it's related to, the idea is when you buy a camera, right, you take, the more pixels, the more expensive, right? But then of course, next thing you know, it converts into JPEG and, you know, and all that. So compressed sensing means when you sense, you compress. So why waste the time, right? So, okay. Levelset, you see, it's heavily used in image processing. I actually would have an example of that. Soft thresholding. This is developed by statisticians. It's also for compression, for example. Okay. Anyway, you look down, wavelets, very well known. This is a famous compressed sensing paper. Now this is GMRS, it's not, it's linear algebra. ROF, this is TV, total variation denoising. I will have an example of that. Wavelet shrinkage, also. My method segmentation. This is fast multipole, very well known. Okay, so I counted maybe 7 or 8 of these. So in the last 20, 25 years, the most cited papers are all in this area. I mean, even to me, it was a revelation. Okay, now the other thing, personally, I look at this. I said, I don't know more than 500 people. I probably, right? And not more than 500 people know me personally, or in my professional field. So most of these people who cite my paper, they're not in my field. I don't know them. They don't know me. They cite it because they use it. Okay, and I have no idea. You know, now with the Google Scholar, you know, you can set an alert. which I have. Once every few weeks they send you this thing, and in different languages. If I look at this, I have no idea who these people are, what they use it for. But that's the beauty and the reward of working on this area. You do something, the jury is out there. They don't have to use your method, okay? And the impact is, this citation, you take it with a grain of salt, for example, for promotion, okay? But certainly in terms of the reach, it's there. So image processing has those phenomena, because today everybody carries an image acquisition device, your phone, okay? And it just is, you have them, and you can do everything with it right there on your phone. That's the idea. Now, I looked up this page. So in the beginning, people ask, we've been doing image processing. You talk to an electrical engineer. God, we have hardware, we have software, we have JPEG, we have all kinds of standards. What do you guys mathematicians bring to the table? Why do we listen to you, right? I think that's fair enough. I think that's a very fair question. So I look up a book. This is a very standard book. It's by Gonzalez and Woods, and then there's a later edition with another person's name. So this is the part of the table of content, okay, of that book. So it reflects, this book is when now? It probably is 10 to 15 years old, maybe 15 years old. So it reflects kind of the approach. This is a very standard book, a very highly cited book. So it talks about filtering in the frequency domain. So image processing is seen as a signal. So, denoising is filtering. You do some transform, you set some coefficient to 0, and, you do that kind of thing. If you want to identify objects in an image, one of the standard tasks, you do what's called morphological image processing. Morphological has to do with shape. You say, what's the object, what's the boundary, and so you do that kind of, it's very direct. For example, image segmentation, I will talk a little bit about it. What you do is you detect points, from points you detect lines, from lines you detect edges, then you detect objects. It's very intuitive, but that's the approach, okay? So now, in 1998, there was a special issue of IEEE transaction and image processing. The first time they published something using this sort of PDE-related topic. So if you look at the topics here, I have two papers here. There's this and there's this, okay? You look at this list, without looking at detail, has nothing to do with this, other than the applications. The whole approach was different. That's what I want to illustrate. So there was a kind of bifurcation transition sort of that went on. And, okay, so please. Okay, so the purpose of my talk is to illustrate, as I mentioned earlier, that image processing and math goes both ways, the new CFD. So going this way, there's some of these things, these mathematical methods or framework that has been applied to image processing in this new way. Okay, and it's not, there will be new method that will be used. So actually CFD PDE type methods. Okay, so it's kind of interesting, the way you design an airplane, the method can be used to process images. That's actually what it is. You see, why? You wonder why? Well, actually, very simple. So in aerodynamics, you have something called shock waves. And that's been a challenge, but that's a nonlinear phenomenon. And that you cannot do filtering. You cannot do a Fourier transform or Wavelet transform and just set things, because those are linear processes, basically. So people have been working very hard to simulate shock waves so that you retain the right shape and the right height and so on. Well, the edge on an image is a shock wave. Mathematically, it's the same. You have a jump, is a discontinuity. So people realized suddenly, 20-some years ago, say, hey, I can use this method. Okay, so there's a term called total variation. I'll talk a little bit. Well, it turns out total variation was a big class of method in doing CFD, in shock wave. So if you go to a AIAA conference, there will be people talking about this. And the same mathematician can go to image processing and talk about that. So I think in a way that's the beauty of mathematics. Once you have the mathematical framework, you can apply them to, you can borrow ideas in one and use it in another field. So another area is calculus of variation. Okay, so some of you know variational functions, the independent variable, the thing, which function will optimize an objective. Well, the way it arises in image processing is instead of looking at image processing as a linear process, you look at it as a variational thing. It's like physics, right? Is that I want to denoise this image. I want to segment this image. I want to do whatever to this image. I define an energy. And the desired result is the thing, the function, or the image that minimizes the energy, right? This is kind of like physics. And how you get to that, that's computation, okay? So obviously calculus of variation will come in, right? Because you're doing a variation. Differential geometry, that actually is a very exciting. Okay, level set is one. Okay, level set is an implicit representation of shape. And it's very powerful. I will say more about it. So you think about imaging, right? You have an image. You want to get some object. You want to deal with shapes in the image. So how do you do it? You can sort of look at it at the micro level. You can look at the edge. I have a jump, and I have these edges. You connect them. That would be one way, a microscopic way to do that. But differential geometry is looking at things at the large, right? It says I have functions, I have level sets. Level set you can do in MATLAB. You can just say basically, forgot what it's called, level set basically. You can extract. And you can then, once you have level sets, you can measure curvature. Right? This is what differential geometry is about. And you can talk about smoothness of shape and all that. And it's implicit. It's implicit. You write down a differential equation that captures the differential geometric properties of the implicit shape in a function. You write down u of x and y, a function, a scalar function, okay? The shapes are represented by the level sets of u. U is equal to constant, okay? And you can describe all the geometric things of that function by writing down a nonlinear differential geometric equation. So it's just a very powerful concept. So by capturing it that way, you can then characterize the desirable outcome of your image processing using the variational principle. So that's another sort of conceptual breakthrough. You then have, of course, because images are non-smooth, most continuous mathematics were based on smooth functions. Sobolev spaces, that's a very, you take a function, you take some derivative, you take some integral of that over some domain, and that sort of characterizes how smooth a function is. And that's very heavily used. Well, you cannot use those functions, those characterization on images, because they're all discontinuous. So for example, if you have a function that is like a straight line, one-dimensional, now you say that's a very smooth function. Well, if you have a function that goes like this, a jump to go there. Now, is that less smooth? In this classical way, it is. But in an image way, it's not. It just has a little jump, that's all. So there's these class of functional analysis, if you will, that captures functions of that kind. And for example, some things called bounded variation. From the name you see. So we don't care whether microscopically, whether derivatives are continuous or anything like that. You say, if a function goes up and down less, that means it's nice, it's regular. And that's the space of bounded variation. And from there, you can derive methods for dealing with images. I think, without even getting into detail, I think you get an idea about what kind of mathematics can be used. Characterization of regularity, representation and smoothness of shapes, how to characterize in a variational way the objective, and borrowing ideas from other fields like CFD to be used. So that's the obvious things. And many people in the beginning were saying, okay, boy, I used to work on CFD. I have a bag of tricks, so I have a new field. I can write new proposals. I can do that, right? Now, if we only stop there, it will be good. You can bring some new idea to this field, but it would not be as exciting. Because what is exciting, I think, is from here to there as well. And that's what CFD did. Because it's so difficult that when you drill in there, you found out new things that you didn't know you needed or you didn't know at all. Okay? So here's some. This is still ongoing. Compressed sensing is one I would credit. Because I was there, Terry Towers at UCLA, Candace was basically he spent his time at UCLA even though he was at Caltech. And it sort of grew out. I kind of know the origin. L1 optimization. basically idea L1, the L2. So most people use L2 because it's nice and smooth, it's like least square. But turns out L1 is the new thing. You've got compressed sensing, everything. But L1, classically, nobody have looked at. People don't know how to formulate them. They don't know the theory behind it. They don't know how to compute with it. So in a way, image processing sort of motivated a lot of new methods over there. Some of those I show in that slide, like wavelet shrinkage, for example. That's an example. And now there are many, many methods. Geometric problem, convexification. Okay, so this is a little bit, so to this audience, I think it's good because you have an optimization department here, if I understand. Am I right? So, okay. Actually, very good because so you have calculus of variation, right? You have this minimization. So you have to compute. Now, most optimization problems are not convex. They have many local minima, okay? I mean, the way it manifests itself in image processing is you have a donut, let's say in an image. And you say segment this. You get the shape out of it. Well, do you get the outside of the donut? Do you get the inside of the donut, or both? So they're all local minima. That simple way. So when you write down the variational principle, it will have many local minima. So this is the problem for the optimization algorithm, right? You get trapped, you so on. So, but turns out because of the difficulty of this, and this is a special class of optimization problem. So people have this device, what they call convexification. So they take a non-convex problem, which most of these imaging problems are. They use some tricks, mathematical tricks, intuition. They convert them into a convex problem, which you can solve. Okay, just go downhill, basically, right? Minimize. Go downhill is a unique minimum. Then from that global minimizer, you can recover a good solution for your original problem. So that's a kind of a new thinking, okay, that these problems motivate. And of course, that technique can be applied to other problems, not just imaging problems. And there are other ideas. So if I'm going to get into a little bit of the detail going both ways. So it depends on how much time I have. But if you are not a technical expert, if you walk away remembering this, I think that's probably, I will be very happy already. I'll be very satisfied, okay? So please, yeah. Oh, one more before I dive into the detail. Because the field is relatively young still, I mean this particular subfield, that I can trace part of the timeline, okay, because I sort of lived through this, so to speak. I started doing this around here. Some of these only started a little earlier, okay? So if you look at the different tasks, denoising, segmentation, inpainting, I'll tell you what, the compressed sensing, they're related. Inpainting meaning you have a scratch old photograph, you want to touch up. You want to paint into the cracks, so it's called inpainting. The ceiling of the Sistine Chapel, you want to recover, that's the idea. Optimization, convexification, segmentation. So these are the topics I mentioned. And you can trace some of the timeline of the important papers and so on. And, for example, Candace, and Tao, and so on. So my point is, it's very compressed. Sort of, in a matter of 5 to 10 years, a lot of new ideas, because it's sort of in the early stage and people come up with a lot of the ideas. And you can sort of see how this goes. And even the journals that were coming out. The special issue I talk about, the SciAm journal that came out. Now there's regular SciAm conferences in this area and so on and so forth. So they can sort of all capture, in this. Okay, a little bit about the challenges. If it's easy, then, it's no fun, okay? So the challenges are this. Images, as I said, have discontinuities. So you cannot use linear methods. You have to devise nonlinear models. Okay, so that's one challenge. Nonlinear is always difficult. And the other one is you have geometric things, and you have to capture them, make the most out of them. Preferably in an implicit way, rather than explicitly looking at edges and connecting them. And you have to devise fast algorithm, because everybody, your panorama iPhone is amazing. It's doing a lot of image processing. And I used to do that myself. It's called stitching. You remember but now it's real time, right? Okay. So it's because it's difficult because of the huge data volume. Actually, you have at least 3 channels, right? RGB, color. By the way, it could be multispectral. You can take infrared. You can do all kinds of stuff in a real scientific case. You have time because you have video, right? So it's just like CFD. So the volume is very big. So it's whatever you do, you have to handle these. So the PDEs in image processing, where do they come in? So here's some of the early work, okay, that play an important role. So the early work, for example, in this paper, very early, they call scale space filtering. So it's still filtering, but you look at scale. You look at an image. So you take off your glasses. I'm short-sighted, so I want to see you fuzzy. I don't have a high resolution, right? So the idea is you think about it in a hierarchy, and for each one, it's a scale. So they define a scale space. It's kind of like Fourier transform. You see what I mean? Okay. So that's the early thinking. Mumford and Shah had a very early method. Mumford, I know many of you, David Mumford is a fused metallurgist, is a well-known algebraic geometer who changed his field overnight to do imaging. So he was using these piecewise smooth functions and associated variational problem. He's one of the early ones who did this. This is an important paper. I think Perona is at Caltech. He was an electrical engineer. And Malik is at Berkeley, is a computer scientist. So they were one of the early people who looked at processing images, for example, denoising images, as heat diffusion. Okay, so you write down a heat, remember a heat equation, UT equal to UXX, remember? Right? So they were saying, okay, so heat equation dissipates, smooth things out. But of course, it smooths out the noise as well as the edges. You don't want that. So their idea is that it's called anisotropic. It says, if you diffuse, when you come to an edge, if you do not diffuse across the edge. You can diffuse along the edge. So it's anisotropic. That's a nonlinear process. So they wrote down, using their intuition, some PDE, highly nonlinear. Okay? Basically, the diffusion coefficient is small when you close to an edge. Okay? You can imagine. That's how it goes. Level sets, I want to mention a little bit. This is a classic paper by Rudin, Osher, and Fatimi using the function space, measuring regularity by bounded variation to denoise images. So, okay, here's a Perona Malik. It's a classic paper by computer science and electrical engineer using PDEs, nonlinear PDEs. So let's look at this. Here's you have an image. Think of it as dark is close to 0, white is close to 255, right? Typically. So it's a function, it's positive function. You can plot it. So you want the denoise. So you say, okay, that's U. I run this heat equation. Okay, if this is divergence. UT equal divergence or Laplacian, right? Divergence of gradient of Laplacian. Okay, so diffusion. If you just do that, everything will be smoothed out. So what they do is I want to have a diffusion coefficient defined in this way. Basically, you can write down any function that when the gradient is large, this should go to 0. So near an edge, the gradient is infinite. So it goes to 0. So it's called anisotropic diffusion. And this works wonders. So that's what caught a lot of people's attention. Caught the attention of pure mathematicians who try to, they've never seen an equation like this. So is it well posed? Does there exist solutions? How to compute the best solution? All that, mathematicians love to do. Okay, so, and it's important, okay? Because basically the engineer, they wrote down the equation and said this is the right thing. So the challenge to the mathematician, is this right? Does it produce good results? So that was an early thing. So here's another classic paper, a little bit later. It's variational. So it's not just writing down a PDE and say, this is how the image should evolve. So this is variational. It's kind of like, for many of us in doing computational linear algebra, it's very familiar. We do regularized least squares. Okay, you try to do a data fit. You measure the error in L2, and then you regularize, because otherwise, for stability. So the only thing is, so you have an image U that you want to recover. You are given a noisy image U naught. Okay, so for example, this is U naught, and you want to recover this. Okay, so K is like a blurring function. So forget about K for the time being. So you basically define the denoise image U as the function that minimizes this functional. You want your U to match the data as much as possible. That's the least squares, right? This is L2. But you want that, well, the simplest one is pick U equal to U 0, and you have a 0 error, right? But you don't want that. You want the one that is without the noise. So it means regular. And one way to do that is to say, to measure this by the total variation norm. The total variation is this. So this looks very much like a Sobolev norm. Okay, so you take the gradient. The gradient in 2 dimensions is ux, ui, right? A little 2x1 vector. Then you take the L2 norm of that. So this vertical thing is the L2 norm. So ux squared plus ui squared. Okay, and then at every point you have ux squared plus ui squared, and you integrate over the domain. Okay, that would be the Sobolev H1 norm. You take the square root of it. Okay, of course. Okay, and so on. So, but here I say no, don't take the square. Just take the sum of the absolute values. Don't take the sum of the squares. Just a little difference, okay? Makes a big difference. Because this one turns out to preserve edges. That's the big difference, okay? So the way they solve it, this idea came from CFD. It's from shock capturing. There's a scheme called total variation diminishing schemes in CFD, okay? So if you take what's called the Euler-Lagrange equation for that functional, you know what? You have a functional, you compute a gradient at every one point, and you want to go downhill because you want to minimize. And if the gradient of this is this. The gradient of this is this, right? Obviously, it's a quadratic. This is a linear function. It's sort of the normal equation for those who study this. And the gradient of this is this. Okay? If this were the Sobolev norm with the square, this would be the Laplacian. So minimizing the Sobolev norm, H1, is equal to diffusion by heat equation. But now with the L1, you have this thing sitting down here. But this actually has the right behavior, because near the edge, gradient U is large, so the diffusion coefficient is small. Right? It's like paramolecular. But this falls out of the variational principle. It's not explicit, okay? It just falls out. And for example, in a 2-dimensional function, you take this, you will get this. And this one, if you use a quadratic functional, you know, if you do sort of a linear model, you will get this. This is sharper than this, the edges. In 1 dimension, it's easy to see. You get this noisy image. Well, this is your data, 1 dimension. If you do FFT, you set the coefficient to 0, you get this. You get what's called Gibbs phenomenon. If you use TV, you get this. All the edges are recovered at the right location. It's like magic. If you do this, it recovers this. Now, it's not perfect, right? The height a little bit, because you want to minimize the variation, so it's obliging. It says, I want to squash them, okay? If you use H1, which is put the square here, you get oscillation. If you do wavelet compression, so this is the lowest order wavelet, this is the higher order wavelet, you still get some Gibbs phenomena, but a little less because it's more local. So you see the advantage. Okay, another task is inpainting. Okay, so inpainting, as I said, is filling in missing information in an image. So again, I said Sistine Chapel, the ceiling. So you hire artists, go up there, and you try to. So what do you try to do? You want it so that people look at it and they didn't know you had repainted it, right? That's the idea. So you want for smooth regions, you want the color to be indistinguishable from the rest, or smooth. So mathematically, for smooth region, you want it to remain smooth. But when you come to an edge, right, like Michelangelo had the finger pointing, you want to respect that. You don't want to smear it out. So, and you want to do that automatically. So, and in this approach is actually very elegant. So let me give you an idea. So it's just like this ROF model I showed in the previous slide. Very simple. So the idea is this. Let's say you have this image, and you are missing this, okay, information. So let's say those pixels are lost in some way, either scratch or lost in transmission and so on. And what you want is to recover this. Now, if you do the smooth fill in, you will get something between the blue and the yellow, right? Because they will be sort of matched up. You don't want that. And you want to do this automatically. So there's a very elegant method you want to do this. So you say, I want to do like ROF, right? Least square regularized with TV. So this preserves edges. But you only know, you only have data, you don't have data in this region. So this means it's the region where you have data, okay? So you say, where I have data, I want to minimize, I want to have the good fit, right, least square way. But however I fill it in, the overall recover image has to have good regularity. This is over the whole domain, okay? So that concept, so it's very elegant here, right? It just like looks exactly like before, except the domain, you just adapt in a natural way. Where I have data, I want it to fit. Where I don't have data, I don't require. I let it have the degree of freedom. But when I measure regularity, I measure over the whole domain. And the algorithm for this is just like the one before. Basically, when you run through the algorithm, you just have a mask. You say, when I come to the missing domain, I don't update that term. You know, it's very simple. It's very elegant, and you can get amazing results. So, for example, you can take this, and you get this back. You notice, right? Over here, you have a sharp edge, the face, but on the face, on the forehead, where it's supposed to be smooth, it's smooth. Where it's supposed to have a jump, it has a jump. Nobody goes in there and says, is this an edge? Should I do this? Is this smooth? Should I do this? None. Completely automatic. That's the beauty, the power of this kind of mathematics for image processing. Okay? Okay, so that's an example, please. So here's another more real-life example. Okay? I was working with this guy, Doug Robley. He worked for Digital Domain. This is way back now. Digital Domain was the special effect house founded by James Cameron, I think, right, the director. Titanic. He made the Titanic, okay? And so they have this in Venice, Los Angeles. They have this house. They hire actually a lot of computer scientists, obviously, and mathematicians to work. So this was a movie. I forgot what the movie is. This is Emma Thompson. Something about her boyfriend, and this is kind of like science fiction. I don't watch the movie. But anyway, it's a little too bright. Maybe can we turn down the thing for just a second, the light? Because, yeah, okay, thank you, just for now. You see the wire here? So in the movie, this actress has a wire harness. And she's supposed to be, it's kind of like science fiction. She was flying through air when they shot it. But when they show it, they want to, in-paint that wire out. This is very, very well known in Hollywood. Okay? So please move to the, oh, no. Let's show the next image, because I want to show you how to get rid of that, right? Okay. So we have this technique, it's called elastic inpainting. It's like TV, okay, so never mind. So you get it out, and this is very challenging because, where it's smooth, where you have her blonde hair, and, all the edges, so boom, all of a sudden it's gone. And you do not have to know precisely where the wire is. You just have to know roughly. Because, if you extend the domain, it will fill it in correctly. Now, there's a limit to this. I always say, if you block off her head, we will not be able to recover her head. Okay? So I mean, it's not science fiction, right? So, okay, I always say that. Okay, please, another one. So we developed some, it's too detailed to show. And for the hair, it's a challenge. Because it's not smooth, right? Hair is not smooth. You have what's called texture. So we developed a technique where when you have texture regions, you will be able to recover that as well as when you recover edges, as well as when you recover smooth region. So this is sort of illustrates some of the challenges. Okay, so let's see another one. So here's one, not the movie now. So let's say you have this. The director said, this is ugly. I want to get rid of this. So I want this. If I show you this, you did not know the origin was this, right? Now, if I show you, maybe you go in and blow it up. You might. Even then, I think it was pretty good. So how did it do it? If you show the next slide, it blows up this thing. Yeah. So this is a blow up. You see the wire, okay? And if you push again, so that's the region. Standards. They say, I want to fill in that region, please. Gone. Okay. You see the hand, the edge of the roof, and everything recover. Okay, so basically you have someone says, use a brush and say, this is the region I want, push a button, and it comes back. Now, this is very, very standard now in Hollywood. So that was the idea of using total variation, functional bounded variation, variational principle. And I hope you see that it's a different way of thinking. It's not looking at the image in the small. It's looking at it as in the large, okay? And you see the power. Okay, now I want to bring in the differential geometric aspect. Okay, remember that was the shape and so on. So I mentioned about these level set methods. Actually, level set method were developed for tracking in computational combustion, tracking flames. The flames in combustion, and how do you follow them? If you watch a flame, it's very difficult. It moves all the time and so on. So, but then it quickly found application in image processing. So Mumford-Shah, my method with Luminita, and so on. So please, next one. So I want to show you Mumford-Shah. That was what the granddaddy of this method. Okay, very mathematical, but it's actually very elegant and simple. So the idea is this: you have this image. You want to find segments of the image. What does segment mean? It means region of the image where within the region the pixels are similar. For example, similar color, similar intensity, right? So it distinguishes the object from the background. That's the idea. Okay, and they are typically separated by edges. Okay, so mathematically, how do you describe this in a variational way? So this is called the Mumford-Shah functional. Okay, you have so S is the function you want to the segment you want to recover. Okay, U0 is this. Okay, so this is S, right? You can see the little smooth patches. So you want least squares. You want whatever you recover to match. Now you want within the segment, you want as smooth a function as possible. Okay, you want piecewise smooth. In other words, that's how you define by segment. But a simple way to do that is for every pixel to be a segment. Then you have perfect match. This is 0, this is 0, but it's not regular, right? It's too fine grained. So you have to add this term. This term says is you measure the boundary of the segment, and you want that as small as possible. So small perimeter of the shape that best match the image with as smooth an interior as possible. Okay? That's the kind of variational thinking, okay, that you do. Now, easier said than done, because you write this down. When you want to, the mathematics, this is a calculus of variation is very difficult, because you have, this is one dimensional lower, because this is the edge, the perimeter of these things. And you mix in, it's very difficult to do. And these are two, Mumford at least, one of the best mathematicians in the last, alive, basically. And they could not completely finish this program. Because what they were able to do is to, for example, does this functional have existence of solution? I mean, easy to write down. How do you know it works? Does it have uniqueness? It does not have uniqueness, because this is not convex. In a way, there are many parts. I told you about the donut, for example. Okay, so they prove things like that. So the solution is actually the set of edges and the S, the smooth pieces. The S is the segmentation. That's the idea. Please, next. Okay, so this is where I came in. This is some time ago. So I knew about Mumford-Shah, but I was not thinking about doing Mumford-Shah. So we were thinking about how to do segmentation. As it turns out, we will implement Mumford-Shah, as it turns out, okay? So the idea is this. The idea, okay, here's actually literally how I thought about this. The idea is, okay, I have an image. Let's say I take a picture of this room. I want to pick out the individuals, right? Now, how do I do that? So actually, I look at this sign. I want to pick out that sign from the background. How do I do that? Well, I'm short-sighted, right? I take off my glasses. I cannot read the letters. But I know, on average, that sign has a different color, a different intensity from the background. That's all I need to know. And then I can pick out, right, that object. So that's the idea. The idea is, for every object, I have an interior, I have the exterior, okay? And within the object, so this is inside the curve, right? And outside the curve, I want to match as much as possible the image. But on the other hand, like Mumford-Shah, I want to minimize the perimeter of the object. So that's a kind of a smoothness of the shape. Okay, that's the idea. Okay, so again, it's like Mumford-Shah. I want to minimize the curve. So the very independent variable is the curve, and you have this constant, the average. So this is the simplest way. So the object is different from the background on average. Okay. Now the way you do it is first of all, how you represent the shape, and this is where level set comes in. Okay. So level set is an implicit representation of the shape. So for example, here's a shape. How do you represent this? You look at the scalar function phi. Scalar. Let's say you say the scalar function is less than 0 on the inside and positive on the outside. So the shape is phi equal to 0. Okay, it's implicit. Okay. Now, just a little trick. You can represent every geometric measure of the shape, for example, curvature, through this functional phi. You don't have to go in the curve and say how much do I vary and measure the curvature. So for example, the normal to the curve is the gradient divided by the norm. Because it's unit vector, right? So that's again, imagine. If I take the divergence of that, you get the curvature. But this is a two-dimensional function. So if you have this functional, and you compute this thing, and you evaluate it at phi equal to 0, that measures exactly the curvature of that level set. So this is actually very implicit. So once you have that, then you can take that functional I've written down, okay? And for example, the length of the curve, you can write it as the Heaviside function of the level set, and then do the total variation of that. Because basically you have 1, 0, and the total variation of that is exactly the boundary, the perimeter. So the idea is that you can write down everything. So this is that curve, that term, you will in number h. And inside means you multiply this term by the Heaviside function, because it's 0 outside, right? So, and you're going to integrate over the whole domain. Outside means 1 minus that function, right, the complement. So you take this, now it's over the whole domain. You take the gradient, it looks like this. It looks like paranormalic, right? You have this functional, and you take this equation and march until everything goes to steady state. And that's your segment. So if you click on these two, so this is even a crazy function, right? It's just some dots. I think you recognize this is Europe at night, okay? And it's very difficult to segment. There's no boundaries, it's just points. But this one you can segment. And this is a galaxy by astronomer. You can see that it homes in and do that. So this is the power, no well-defined. It's sort of region-based. Forget about this. No time. Anyway, you can extend, you can do brain MRI segmentation and all that. This one, okay, I just say a word about it. I will not elaborate. But when this came out, the people who do Fourier transform, wavelet transform is generally called harmonic analysis. They said, wow, this PDE guy can do geometry. Can we do geometry? Then they invented this field called geometric harmonic analysis. And you see curved lists, all these LETs, wavelets. But harmonic analysis plus geometry, that sort of became a field by itself. They want to integrate. Whereas this geometric PDE sort of has it implicitly. Okay, so that's another view. Okay, so this is L1. Okay, so this is another area now. Okay, this is okay, please. Almost time.
Almost time.
Okay, let me fast forward. Let me fast forward. Yeah.
Okay. Yeah.
Yeah. Okay, let's do this one. This one is fun. Okay, this is related to compressed sensing. So we were doing this before we knew compressed sensing, the term. So the question is, do you recognize that person? No, right, obviously. So what it is, this image, you take an original image of a famous person, you compute a wavelet transform, and you set, I think, half the coefficient to 0. And that's what you get. Half meaning fine scale, coarse scale, and you just randomly, you set 50%, 0. And that's what you get, right, if you recover. Now, I want to recover the original. I say impossible. Impossible, right? But turns out it's possible. The reason is, when you do this wavelet, there's a lot of coloration, right? You have fine scale. This is not recovering the person's head, right? Remember, it's different. Because you still have some of the information in the wavelet coefficient that you retain. So how do you recover? That's the idea. That's a key concept. Very simple, using this variational principle. Basically, you have a constraint optimization problem. You say, I want to recover the image U so that if I do the transform, do the wavelet transform, it will match those coefficients I still have. That makes sense, right? That's what I have. I do. But the overall image gotta have as regular as possible. And in this case, I measure by this TV norm. Okay, very elegant, right? I have missing things. I said, when I have the data, I want to match. When I don't care. I let it have a degree of freedom. And then overall, after you recover, I want that function to be nice. Actually, very sort of high level. And that's what we do. Now, the other thing you can do is, of course, you can say, you can put in the least square term. But this one has no parameter. There's no parameter to tweak in the image. You know, unlike many models, you have many parameters. This one, no parameter. Okay, if you go to the next slide. So that's our famous former president in the US. Okay, so that's the original image. This is the one you saw. This is actually what you can recover. I mean, at least at this point, you can kind of, 50% is a lot, right? You can recover. And if you have a synthetic image, this is 50% missing, and you recover. You can even recover some of the texture. So this is the extreme case, right? So if you go to the next slide. So this is compressed sensing. So we actually did an experiment. We took this as a test example, just a block, a square block. And if you you set 50% of the coefficient to 0, and you get some crazy thing. I mean, you get it there. But you can still see, you can kind of trace out the edge. Okay, the coefficient that are retained has some edge information. And if you do this thing, you get this. This is exact recovery. If you do a cross section, it looks like this. Okay? So we said, wow, that's great. This is the PSNR, the signal to noise ratio peak. So basically, the higher the better. And this corresponds to this. So if you do our method, you get how many dB? I don't know, this is huge, right? So you basically, by computation, you recover a huge amount of missing information. That's the idea. And, well, it turns out several years later, this is called compressed sensing, okay? The compressed sensing is exactly this, but you can prove. You can prove under what condition you actually get this back. The rest is history. I don't have time to go into compressed sensing. So compressed sensing is nothing, in fact, if you go to the next slide I might have. Yeah, this is compressed sensing. This is a famous paper. By the way, won both him and him the Waterman Award. Well, for him, it's one of the many things. For him, it was the main thing. Okay? So, yeah. Well, many of you, I think the mathematician would know. Because, there's a Green-Tau theorem. But he got the Waterman Award after him, 2 years after him. So image processing is actually more visible, in a way. So compressed sensing is basically this. It's you have a signal, you have a measurement, you have data, and you want it to match. And then you minimize the regularity. Typically L1. That's the key, is L1. And if this is gradient, then it's exactly what I showed in the previous slide. Right? Basically, if this is a gradient, it's TV, and you want to measure the coefficient that you have in the transform space. So the compressed sensing problem, if you choose a regularity this way, is exactly the TV wavelet inpainting. But you can prove under one condition this actually works. So this has huge implication, for example, in medical imaging. If you go in for an MRI scan, right? Usually, I don't know what it is now, you have to sit there for half an hour, with this magnet going. So the idea is that if you measure you take fewer measurements. So you can get out in 5 minutes instead of 30 minutes. And you can use computation to recover. That's better, so that's the power of this. Okay, so now I have to probably wrap up. Okay, forget about this. This is a little technical, but for those optimization department people, I apologize. This is where convexification was useful. It's a little technical, obviously. This has to do with. Maybe I go to the let me do this. Yeah, I just do this, right? Yeah. I want to show you one slide. No, yeah, this is convexification. There's some mathematics in here, but I want to show you. Yeah, this slide. I think this is one of the last slides. So when people were doing, this has to do with the algorithm, right? People want to compute fast, but you have non-convex optimization problem, so you cannot be too greedy because you can quickly compute the wrong solution, basically, right? So that's no good. So people were struggling with methods, and as it turns, so they invent new names. For example, Bregman. Where is that? Bregman. I never heard of Bregman. My colleague Stan Osher sort of discovered this. Some of you know Don Goldfarb. Some of you know, a very well-known, So they say, hey, Stan, I know about this Bregman thing. Oh, that's great, So they did this. So there are these primal-dual method, split Bregman. Well, it turns out there's nothing new under the sun. Because for every one of these methods, there's some classical method. For those of you in optimization, all of these methods. But people did not know. See, to be fair to people who do this, I was among them, okay? You see, my name is here. So we, to be fair to myself. So when people develop these classical methods, for example, in many optimization, material science, in CFD, they were looking at smooth problems, L2, H1, And these methods like augmented Lagrangian, they work, but they're actually quite not that efficient. You have to bite the bullet and crunch the numbers. Okay, but it turns out if you apply them to L1, they work like a wonder. And people really did not know that. I think, Tom, is that fair enough to describe? I know you have some optimization expert here. So in a way, because of image processing, people discover that these old horses have some new tricks. Ponies, whatever, have some new tricks. So, yeah, so in fact, for every one of these, you have a counterpart. So I show this in this talk, and the optimizer in there, like Nick Trefethen, say, oh, wow, this is great, So I haven't wasted my time, in graduate school learning this stuff, okay? So I think this is very true. So when we study, in that way, there's a philosophy of basic science. You study them because they're interesting, they hang together. You don't know how they're going to be used. They might turn out to fade out. They may resurrect in different forms that you had no idea. This is an instance of that. In a way, if we didn't know this method, it would be difficult to invent them as the need comes up. Okay, I always compare it to GPS. I think GPS is a very good example of where basic science is needed. I said if you ask a company, okay, BlackBerry, okay, Sony, whatever, you say, invent the GPS, they will never be able to do it, okay, on the spot, because it requires developing the atomic clock. It requires knowing the Einstein theory of general relativity. There's no way. But the people who do this, they did it because it was interesting, because of the, it fits in, basic science. And then when you want to develop this, they're just right there, okay? And I think that's an important message, I think. While application of technology is important, developing the basic science is also important. Both are important. And we see it in small, in this one particular example. I think I make that the last slide. So I think the last slide, I think I have an arrow going one way. I think I show you a little bit of a glimpse of the arrow going the other way. The thing going both ways still going on. And I think there will be, all of us can contribute to it going both ways. So I feel I should be doing some more of this, spending more of my time, but I don't have time. I'm actually doing trying to restart a little bit of this, but it's difficult, I can tell you. Okay. Thank you very much for your attention.
Thank you, Tony.
Do we have time for any questions?
Questions from the audience?
I'll ask you a question. So in a few of the slides, you had 2 terms or 3 terms, and one of the terms had a lambda.
Yeah.
You never talked about it.
Yeah. Right. So except for that image inpainting, there's no parameter, okay? So that's why I pointed out. Yeah, but it's difficult. Some of those parameters are intrinsic to the model. So for example, image segmentation. You have a term that measures the L2 error inside the region, And then you have something that measures the length of the shape, right? So it's basically surface to volume, right? This is a basic mathematical concept. And that's like scale. Now, if I want to segment this room, now, for human, it's kind of natural to want to pick out the human, but that's only one of the scales. Maybe I want to pick out the polka dots on my tie. How do you know? So that parameter sort of tells the model, I want the polka dot rather than your face. So that's part of it. Now, some of the other parameters are computational. Like Augmented Lagrangian has a lot of parameters, right? So you have to separate those two out, okay? So typically what people do is for a particular class of applications, let's say you're looking at faces, you then play around, or medical imaging for the brain, you play around, then you kind of know the parameter set for that kind of images. I don't believe there's a universal set, because that would make it less interesting, frankly. If it's too universal, it cannot be good for any particular thing. So that's my answer to that.
A bit of playing around for most of the problems to get the parameters right.
Yeah, in a way, it's needed. I mean, I'm sure in most of the applications on your cell phone, there's these parameters that some engineers set. Okay, so, and sometimes it can fail, right? Yeah.
Thanks for a very interesting talk.
Thank you. Yeah.
I'm interested in the computational side of it, and in particular the complexity of computing the functions that you deal with and scalability. So if I have a database of 1 million images and I'm trying to do some, how do these techniques scale up?
Yeah, they don't scale too well. Okay. Let me give you an example. Well, first of all, you look at the PDE approach, right? So what's the complexity of solving a linear heat equation? That actually is okay, because first of all, you can do a Fourier transform and just solve it in a regular. These domains are nice, typically in images, but they're highly nonlinear. So at best, you have n pixels. At best, you can get n, but you'll never get n. Okay. Hopefully, you don't get n cubed or something. You get n squared, or maybe n log n. So that one. But let me give you an example. Segmentation is more difficult. So I had it on one slide, but I did not go into it. So it turns out there's another approach of segmentation, and that is embedded in a graph optimization problem. Actually, that's who would have thought? This is the way. So it turns out they are all related. So you can embed the segmentation problem in a graph, and so it becomes a mean cut, for example, of a graph. And you know the mean cut, right? So there's the Ford-Fulkerson algorithm, for example, and people do use that. So those are, they're not NP complete, perhaps, but they are not easy to solve. Okay, so I think the people are coming to the realization that the continuous and the discrete are really the same. This is another lesson I learned when I started in computer science at Stanford. Basically, this computer scientist said, we're the discrete people. Anything continuous, let the mathematician do. Literally, that was actually the view. We had to learn graph theory, calculus, who needs it? Differential equation, not irrelevant to computer science. I mean, literally, that's the plan. Well, today, anything to solve the problem you want to learn, okay? You have topologists doing big data, okay? You know who I'm talking about. You have, anything that works. So for those of you who are young computer scientists, I say, learn some math. And I think because you're under one roof, that actually helps, because you don't know what you're going to need, and you will have an edge. If you know a bit more tricks in your pocket, don't let the ideology drive you. And I lived through that ideology. Okay, yeah. So.
Okay, so thank you. So let's thank our speaker again.
Thank you very much.
Present a little small gift to our.
Wow.
Speaker. So our director Mark is right. Okay, so we'll present a nice souvenir to our distinguished speaker.
Well,
thank you very much
for a wonderful talk. And we have I noticed you brought your coat, so I do have to pull one thing out of here. We do have a few traditions. This is the 10th year of the Distinguished Lecture Series. But We have one tradition, which is
Coat hanger?
we give a specially carved coat hanger
Oh, now what's oh wow, thank you very much.
from the University of Waterloo.
Wow. I can segment
The
this.
David R. Cheriton, and all the letters there, DRCSCS, David R. Cheriton School of Computer Science.
Okay, very good. Thank you very much.
So,
Yeah.
So thanks again, and there are a number of little things here as well.
Thank you.
So, okay, thanks again.
Okay. Wow, smells good.
And it smells nice.
Yeah, yeah.